Today's video is on sodium halides. Okay, firstly we have to look at the oxidative power of the halogens to understand the reactions with the sodium halides. So first, what is oxidative power? Oxidative power is how readily and strongly the halogens accept electrons. And this is mainly down to electronegativity. And so the most electronegative halogen is fluorine, meaning fluorine has the highest oxidative power because it accepts electrons more strongly. The next is chlorine, bromine, and then iodine. And this is because as you go further down the group, the radius of the halogens, as you go further up the group, the radius of the halogens is smaller. So fluorine has the smallest radius of the halogens, and this is because it has the smallest number of energy levels. And the smaller the radius of the atom, the larger the electronegativity, because obviously the electrons will be closer to the nucleus and the nuclear charge will be, nuclear attraction will be stronger. And for the purposes of the sodium halide reactions, sulfuric acid is in between chlorine and bromine in its oxidative power. Okay, first we look at sodium fluoride. And this is the equation for sodium fluoride's reaction with sulfuric acid. So we see here sodium fluoride in its solid state reacted with sulfuric acid, concentrated sulfuric acid to be precise, that makes these two products. But if you look closely, you can see if we put the equation into ions, that actually, even though this is a displacement reaction, there is no change in the oxidation numbers. So if you look at both sides of this equation, you can see that no change in their oxidation states have actually changed. And this is because fluorine has a higher oxidative power than sulfuric acid. So this means that the sulfuric acid cannot take electrons from the fluorine, leading to no electron transfer. So even though it is a displacement reaction, there is no change in the oxidation numbers. Next is sodium chloride, and this is the equation for sodium chloride's reaction with concentrated sulfuric acid. And you can see we get these two products. But again, if we look at this broken down equation of the ions, you can see that this is still a displacement reaction, but there is still no change in the oxidation states. And this again is because chlorine also has a higher oxidative power than sulfuric acid, like we saw in the other slide. So sulfuric acid cannot take electrons from the chlorine. And this is because chlorine, again, is more electronegative, meaning it has a higher oxidative power. So now we move on to sodium bromide. And this is the equation for sodium bromide's reaction with concentrated sulfuric acid. And you can see that we get bromine as the product, as well as sulfur dioxide and sodium hydroxide. And bromine has a lower oxidative power than sulfuric acid, like we saw in the other slide again. So the transfer of electrons does in fact take place because this sulfuric acid has a higher oxidative power, so can take electrons from the bromine. And so let's break this down into this ionic half equation. So you can see that two bromide ions react in this reaction to form a bromine molecule, releasing two electrons at the same time. And these 2 electrons actually go towards the other part of the reaction, where the sulfur from the sulfuric acid takes these 2 electrons and makes sulfur dioxide. So you can see that sulfuric acid plus the sodium ions plus the 2 electrons released from the bromide ions creates sulfur dioxide and sodium hydroxide. And this equation is purely formed from the rest of the reactants coming together once we have formed our electron transfer of bromide ions to bromine. So this is our equation again. And you can see that the oxidation state of sulfur before the reaction takes place is +6. And after the reaction, our sulfur actually has a oxidation number of +4. And this is because it has taken the 2 electrons from the bromide ions in the reactants. And this is not a massive change in the oxidation state. And this is purely because the oxidative powers of bromine and sulfuric acid are actually quite similar. Even though sulfuric acid is slightly higher in its oxidative power, they still are quite similar. And lastly is sodium iodide. And this is our equation. You can see we have our sodium iodide plus our concentrated sulfuric acid. And these are our products. And iodine does have a much lower oxidative power than sulfuric acid. So it loses electrons very easily to the sulfuric acid. So you can see here in our half ionic equation that 2 iodide ions go to an iodine molecule and 2 electrons are released. And because we have 8 sodium iodide moles in the reaction, this has to happen 4 times to get these 8. And then our second equation, you see we have our 8 sodium ions, our 8 electrons created from this reaction that happens 4 times, so 8 electrons are produced, plus our sulfuric acid gets our 2 products. And if we look at the oxidation state of sulfur again, you can see in the reactants, the sulfur has an oxidation state of +6, and afterwards the sulfur has a oxidation state of 2-. And this is because the sulfur is first reduced to sulfur dioxide, and then it is which has a oxidation state of +4, like we saw in sodium bromide. And then it's further reduced to just sulfur, which in its elemental form has an oxidation state of 0. And finally, it is reduced to hydrogen sulfide, which has our 2- oxidation state. So you can see that is how sulfur has been reduced to 2- from 6+. And the difference in the oxidative powers of the sulfuric acid and the iodine is so much larger than the difference in oxidative powers of the other reactions. And this is why we get such a massive difference in the oxidation states before and after the reaction, because the difference in oxidative powers is much larger.